Welcome students. In today's class and in this week specifically we are going to talk about initial and boundary value problems. So essentially the properties of those problems. So essentially let me put it by writing it like this: initial and boundary value problem. Okay, so essentially what it means is for heat equation, you see, if I am writing it like this, so the equation is this: ut minus Laplacian of u equals to f. That is in gamma omega t. Omega t, as you guys already know, it is omega cross open 0 t closed. Okay, and t is positive, of course, it's given to us. T is positive, and u, that is equals to g. G is some continuous function on gamma t. Gamma t is what? This is the parabolic boundary, right? And so this is the parabolic boundary. I hope you all of you remember what parabolic boundary is. So essentially what it means is, that is, let me write it properly what this means. It will make it more clear. U of x0, this is equals to g of x, okay, or g of x0 essentially. This holds for all x in omega, okay. And so on the the baseline x equals to 0 and t equals to 0, on this line t equals to 0, and the bottom part u of x0 is g of x0 and u of xt. So this is the bottom part, and u of xt is g of xt. Okay, u of xt is g of xt. This holds for all x in the boundary of omega and t between open 0 t closed. Clear? So this part is the vertical part, vertical sides, right? Okay, so that's the property given to us. I want to study the mean value property for this problem. Okay, let's say that, let's call it to 1. So let's say for this problem, what I mean by this is, let's say the question boils down to this: let u is C21 omega t, or I mean for now you can just assume it is continuous in omega t, solves 1. Okay, now can we have a mean value property like a Laplacian? Okay, that's the question. So essentially the question is this: if you have, so you remember in Laplacian, what does it Laplace equation when we did? Okay, so just a small recall, let's just do it here, recall. So Laplace equation, what we did is this: we saw that if, let's say, you have a continuous function in omega, u is a continuous function in omega, and it satisfies this equation. So u of x, okay, less than so this is equals to the mean value of u over the ball, let's say ball bxr u of y dy, and of course you can also have the boundary. So let me write it down. So this is del bxr u of y, okay, dy. So this is equals to this, and which is equals to, let's say, it's fine. So this is the mean value, okay, of u. Okay, this is the mean value of u. So essentially what it is saying is, if you want to calculate the value of u at the point x, you just look at the mean value of u in the ball surrounding x. Okay, so that is going to give ux, and this is if and only condition, right? So if u is continuous and ux is looks like this, that will imply that u is harmonic. Okay, u is harmonic, and vice versa. If u is harmonic, then of course ux will look like this. Okay, so that we saw. Now here, whenever we say mean value property, so this is a exclusive property. So let's look at this thing. Let's put it like this. So a small note. Note is this: u has to be, you see, any harmonic function for Laplacian u equals to 0, Okay, any u satisfying these things. So essentially, you see, mean value property is an exclusive property of a Laplace equation. That is what I am trying to say. So maybe I can put it this way. Okay, uh, okay, a mean value property. Let me write it put in this way. Mean value property is an exclusive property, exclusive property of the Laplace equation. Okay, so when I say exclusive property, what do I mean, and what is the mean value property? I mean this. So the average of u over balls. These are the average. I mean the usual balls which we talk about in Rn, right? Our Euclidean balls, B x r. Right, now the question is this. So here, whenever in heat equation, whenever we say mean value property, what do I mean by that? Because we know that the harmonic functions are the only functions for which mean value property can hold. So essentially here there is a small thing which we should look at is this. See, that let's say that a small observation, let's say observation. Okay, so this is, let's say that y is in bxr, bxr or on the boundary. I mean it does not matter here whatever what we are doing here. So okay, so sorry, if y is on the ball ba of xr, is in the ball b of xr, okay, or on boundary. So all of this is also true for when we are doing for the boundary, okay, going for the boundary. So this will imply mod x minus y less than r, right? And this will imply this thing, yeah, and that will also imply that mod x minus y, okay, whole power minus n, that is less than greater than equal r power minus n, okay, and that this, if you multiply a constant here, positive constant, which is more specifically 1 by n alpha n, okay, 1 by n minus 2 alpha n. So essentially that constant. So if you multiply it by 1 by n alpha n minus 2, okay, and mod x minus y whole power minus n minus 2, yeah, minus 2, this is greater than 1 by n alpha n minus 2 r to the power minus, sorry, r to the power n minus 2, okay, n minus 2, okay. So see, what is happening here is this. One second, let me put it this way. N minus 2 or to the power n minus 2. So what is happening is this. What is this thing? This is the fundamental solution for n greater than 3. I mean you can do it for n equal greater than 2 also, n equals to 2 also, no problem. But for here I am just assuming n is greater than equal 3. Okay, now so what is it? This is the fundamental solution, phi of x minus y. This is essentially, this set is essentially this set, no, 1 by n alpha n minus 2 r power n minus 2, right? See here, when we want to modify our mean value property for heat equation, the only modification we can do it in is in this ball, right? I mean, other than that, what ux is defined in, u is a function which is defined in the heat. I mean, that's the solution of the heat equation or Laplace equation, whatever. Yeah. See, the point here is this ball. This is important. This is the thing which we need to modify, and that is why we are looking exclusively at what is so special about this ball. See, if y is in the ball, then the fundamental. So for a fixed, of course. Let's say you fix a x first, okay, and for a fixed x, if y is in the ball, then the fundamental solution at the point x minus y is greater than 1 by n alpha n n minus 2 r to the power n minus 2, right? That is always there. And the great thing about this is, let's say this is on the boundary, yeah? Let's say this is on the boundary del b, then it will be equals to, right? Then the equals to sign will be there, equals to sign will be there. So essentially, in that case, what can you say? You can say that, so let me put it this way, it will be much better. The sphere okay, in case of Laplacian, del b xr, okay, del b xr, are the label sets of the fundamental solution. Fundamental solutions of the Laplace equation, right? See, what I meant by this is, uh, let's say that is, we look at the boundary. I mean, if you can of course look at the ball, I mean interior of the ball, but for now let's just assume it is on the boundary. If y is on the boundary, phi of x minus y is equals to this thing. Now if you change r, let's say r equals to 1, r equals to 2, so phi is equals to that particular constant, right? It will be a constant. Phi is equals to a constant. So essentially what what does that mean? It means that if you are taking y to be on the boundary, so basically any boundary, okay, a boundary of a ball, you can think of that, okay, any boundary, so the sphere, essentially the sphere, you can think of the sphere as a label set, right? That is what it means. So essentially you see, I mean I did it the other way. So if you have a fundamental solution, phi of x minus y, okay, phi of so what am I saying? I am telling that if you have a fundamental solution, let's say given y, let's say fix a x and look at phi of x minus y, okay. Of course, now what you are going to do is phi of x minus y. So you look at the if you want to find out that what is the relation between this particular function and the spheres, yes, and the spheres, then you see, let's say this is equals to constant, okay, so the level sets of phi, so those are actually the spheres del bx. That is what we are trying to say here, and that is very, so that is what I did in the other way. So if phi of x y equals to some constant, then you understand that, I mean, essentially we are looking for the we are aiming for the boundary, okay. So this is the idea behind generalizing the mean value property of fundamental solution. So what we are going to do is this. So let's say this suggests, let me write it this way, this suggests, okay, the label sets of the fundamental solution okay, phi of x minus y. So here it is heat, so x minus y, and you have t minus I don't know, maybe tau or something, let's just write it as we'll use it later, maybe used, okay, in case of heat equation. Is this clear? So essentially what am I saying? I am saying that I mean, you can think of the, now look at the fundamental solution of the heat equation and look at the level sets of that. That will correspond to some function, some set, right? I want to look at the mean value of u over that set, okay. So the definition, okay, the definition is for fixed x in Rn. You remember we have always fixed x in Rn and t positive, okay, t and r positive, t positive, r positive. We define this r is basically the boundary, I mean, in Laplacian we have that radius of the ball. Here similar kind of thing. We define E of x t r. This is defined by set of all those y and s in Rn plus 1, okay, such that s is less than equal t and capital phi of x minus y t minus s greater than equal 1 by r power n, okay. So this we are defining. How we are defining this thing? First thing first. So what is EXTR? It is the set of all those points in Rn plus 1. So see here, I mean, I am not putting any specification on what S is. It can be negative. Please realize this thing. S is in R. Y is in, of course, in Rn, right? Y is in Rn, but it is a set of all those Y and S such that S is in R. So essentially, S is the only. The property which I give is S is bounded by T. This has to be true, right? See, S greater than less than equal T is it's a necessary condition to define this set, because otherwise this particular phi will become 0, right? Because if T minus T, this particular variable is negative, then phi is 0, and we are basically saying that 0 is greater than equal some R3 or n, the set, that set is going to be empty. We don't want that. So S is of course bounded by T, but the thing here is S can be negative. See, S is in R. So this is what we are choosing. This is a set. And where are we are getting this thing? Phi is greater than equal 1 by R power n. So this is just a motivation of that thing. See, in Laplace equation also phi is greater than equal 1 by the level sets, right? Okay, 1 by R power n minus 2 kind of thing. Here it is coming. So in this case, we are just assuming, saying that this is greater than equal 1 by R power n. Okay, so the fundamental solution. Okay, so that is the same kind of idea, the same kind of motivation here. See, here this is not given anywhere. Please realize this. This is from our motivation. We are defining something like this. This is just a motivational thing. Next thing, what we are going to do is we are going to specify that such a definition. If you define a set like that using the idea from Laplace equation, that set is a viable set. Okay, and on this set you can actually talk about the mean value property. Okay, so let's look at what exactly is this thing. So property 1 of this set. So what is so special about this set? So this set, this set E of XTR, okay, is called the heat ball. Okay, is called the heat ball. Clear? Okay, and is a region in space time, right? It's a region in space time, and if you look at it, can you guess what is the the boundary of this particular set? Okay, space time, the boundary of which is a label set of phi of x minus y t minus s. Okay, if you remember here, in case of Laplacian, see, what is the boundary? The boundary of the ball. Okay, here in our usual ball, boundary of the ball. Okay, so that is essentially the label set of the fundamental solution. Here also the similar kind of thing is happening. Okay, so essentially, the boundary, okay, of this heat ball. This we will call it a heat ball. Okay, this is not specifically a ball. It will look like that. Looks something like this. This is the point. This will be xt. Okay, so this will be on the boundary. Yes, this will be on the boundary. See, the boundary of which is essentially, what am I saying? I am saying that if you look at the label sets of the fundamental solution, that is going to be the the boundary del xr. Okay, so that is del xtr. Okay, xtr, of course this is not xr, xtr. This is the level sets of phi of x minus y t minus s equals to some constant. Okay, so the boundary is essentially this. Okay, you can see, right, for some r, let's say something, r equals to 5 or something, so phi is equals to 5. If it is a boundary, will be equals to at that case, right? So phi equals to, like, say 1 by 5 power n or something. So yeah, that's a constant. So phi equals to constant. So you are basically looking at the boundary level sets. Yeah. Okay, so that is there. This is the heat ball. Now, you see, note there are some small things which we can actually specify here. Okay, so note that phi of x minus y t minus s is greater than equal r power minus n. If I am writing it like this, that is equivalent to saying e of xt comma r is the set of all those y comma s in Rn cross R such that, okay, I am writing some stuff here. I will explain where all of this is coming. T minus r square by 4 pi, okay, less than equal s less than equal t, and psi, okay, this is a new function psi. This we will define later. X minus y times s minus t. This is greater than equal 0. Okay, so that's your set. Now, what is psi? Where, let me write it here, maybe it will be better. Where psi is defined by this, I am writing ys. You can just write it in other variables also. That's not it's nothing special about this variable. Okay, see, this ys has nothing to do. You can just change it to z, some theta or something. Yeah, it doesn't matter. So basically, psi will look like this: plus mod y square by 4s minus n by 2. Okay, log minus 4 pi s. Log of, I am not putting a mod here. Please remember, this is. So how is psi written? N log r. R is always positive. You don't worry about it. R is positive. So n log r plus mod y square by 4 pi. What is mod y square by 4 pi? There is nothing to do. Mod y square by 4 s is okay. Okay. So yeah. So mod y square by 4s. Yeah, that is fine. Okay. Minus n by 2 log of minus 4 pi s. See here, this s, whenever I am defining something like this, it is already implied that s has to be negative here. You see, because if it is 0 also, it is not defined. So s is negative in this case. Okay, s is negative, and that is fine. You see, that is fine. Okay, so essentially, this is the psi. Now we are going to, I am going to motivate how this thing and this thing is equivalent. So basically, xe actually looks like this. Okay, e looks like, you can actually rewrite e like that. That's what I'm saying. Right, now how do we rewrite this thing? Okay, now where are we? Okay, so how do we rewrite it? Okay, so 1 by 4 pi, let's just write it, phi is greater than equal r by n, r to the power n minus n. Okay, what does that mean? So this power n by 2 and e power minus x minus y square by 4 t minus s greater than r power minus n. Okay, that is there. So that will give me r power minus n is less than equals to 4 pi t minus s whole power minus n by 2. Right, I can write it like this. So essentially, I am removing exponential. See, this exponential, this is exponential minus a positive term. T minus s is positive, x minus y square is positive. So exponential a positive term. Okay, so I can actually bound it by 1, right? So exponential minus x minus. So what is the maximum it can take? The maximum it can take is 1. Okay, sorry about the plane. So this is t minus s. This is always less than equal to 1. So this is for x equals to y, that is taking 1. Okay, so the maximum value of this is 1, so I can bound the whole thing by 1. So r to the power minus n is bounded by 1. Okay, so it is there. So what does that give me? It gives me 4 pi t time minus s, that, okay, is always less than equal r square. Okay, and that will give me t minus r square by 4 pi, okay, is less than equal s. Clear? Yes. So this is why I am coming out with this thing. See, s is always less than equal t, that is there, and it is s is greater than equal t minus r square by 4 pi. Okay, t, so, or the other way, I mean, you can write it. Okay, s is greater than equal t minus r square by 4 pi. Okay, right. And we also have another property. You see, exponential minus x minus y square by 4t minus s, the fundamental solution, the exponential part of the fundamental solution. This is greater than equal r power minus n 4 pi t minus s whole power n by 2. Right? That is true. So that, if that is true, that will give me r power n is greater than equals to exponential minus x minus y square by 4 t minus s. Okay, okay, I am taking this thing there and I am putting one second, what am I doing? Yeah, okay, that is fine. No, let me write it properly. So now, since this is true, okay, what does that mean? See, from here I can take the logarithm, the natural log on both sides, right? Okay, once I take that, what will be there? This is n log r. If I take it here, this is n log of r, okay, minus this property n by 2 log of 4 pi t minus s, okay, and you have minus x minus y square by 4 t minus s. This is greater than equal 0. Clear? I am taking log on both sides. This is log of r to the power minus n plus log of this particular thing. Okay, so I am just taking everything on the other side, and you have here log of this thing is minus x minus y whole square by 4t minus s. So all of this, if I am putting it together, this is greater than equal 0. So if you look at it, this particular thing basically is psi of x minus y t minus s is greater than equal 0. That's what it is written. You see, psi of x, see, x minus y and y minus s, here there is nothing special. I mean, you can write x minus, see, psi is symmetric about x minus y. So basically, psi of x minus y, psi of y minus x is essentially fine, but you can't change t and s. Okay, you can't change t and s. So here I wrote it like this. See, here this psi, if you replace, you see here this minus n by 2 log of minus 4 pi s is there. See, I can write minus 4 pi s minus t. Okay, so this variable can be negative. Okay, so I will write it like this: x minus y s minus t. If you I mean, this is fine. Just check 1 second, just take your time and check whether this part is fine or not, please. Okay, so you take, I mean, you replace these variables with x minus y and s minus t, and you just check that whether what I wrote is fine or not. Okay, this is how this E of xtr is coming. So this is another formulation of a heat ball. Okay, now let's look at some other properties. Yeah, so another property of a heat ball property. Okay, so before I move on, one small thing which I want to tell you is this: there are some parts of the proof which I am going to assume. Okay, so I am going to while doing, so let me put it this way. So while doing mean value property, some parts, some results will be assumed. Okay, this is not results from PDE. Okay, this is some results from several variable calculus. Okay, so some results will be assumed, and some you have to check. You have to check yourself. check yourself. Okay, so this is standard, that's checking yourself smart, but the thing is I never took any results to be assumed up till now, but today we are going to take a small liberty and assume one result which is absolutely, I mean, which is not possible to do it in this class. Yeah, so that I will assume, and you got 2. So okay, so let's look at the property of a heat ball. One property is it is essentially a translation. So you can just think of heat ball as this. R is the property xt. Okay, so E of xtr. So the heat ball around a point xt is nothing but the translation of I mean the unit ball 0 0 r. Okay, the translation of the heat ball around 0 0 by xt. So if you translate it to the xt, then that will be extr. Now where okay, E of 0 0 r, this is given by ys in Rn cross r such that minus r square by 4 pi less than equal s less than equal 0 and mod y less than equals to root over minus 4 s in log r minus n by 2 log of minus 4 pi rs. Okay, now where am I getting this? I mean, I'm not getting it from anywhere. It's just a problem. I mean, if you put E of 0 0 r in this thing, if you just put 0 0 in place of x and in place of t, if you just put 0 0, you are going to get this property. I mean, this is very straightforward. Okay, so there is nothing to do. Yeah, you do not have to check also. This is fine. Don't worry about it. Okay, so and this you guys should check the psi, the function psi, this function psi of ys is n log r plus y square by 4s minus n by 2 log of minus 4 pi s. This function has this beautiful property of translation. So this is lambda y lambda square s and lambda r. If you just if you scale it, property of not translation, scaling, if you scale it with this particular scaling, then that will be psi of y s r. Okay, this is for every lambda positive. So please check it yourself. I mean, it will take 30 seconds at most to check it. No issues here. So please do that. Okay, so now that we have some idea of how what the heat ball is, I mean in this case, yeah, in our case, what the set is, let's write down the heat equation. Okay, so mean value property for heat equation, mean value theorem for heat equation. Okay, so what is the theorem here? Theorem says that let u is in C21 omega t solves the heat equation, then the mean value property holds. So what does that mean? Then okay, u of xt, so u at any point xt is given by 1 by 4 r power n double integral e of xt r u of ys, okay, mod x minus y square by t minus s square dy ds. Clear? So this is it's not exactly the kind of mean value property. You do realize that kind of property which we did in Laplacian may not work here. Okay, so here u of yx has a friend kind of, which is given by this term mod x minus y square by t minus s whole square. These u with this thing, if you integrate it, then it is 4 r power n u of x t. Okay, again sorry about the noise. Okay, now we need to so this holds, so then this holds for all e of xt r which is contained in omega t. Okay, so this is holds for all of that. Now, so let us look at the proof of this theorem. Yeah, let us look at the proof of this theorem and then we will go from there. Okay, so the proof. If you remember the proof of mean value property for the Laplace equation, we started out with the phi of r, right? Okay, so let's start here also. So proof is, let's start, define phi of r is 1 by r to the power n integral xi tau in e x t r. Okay, e x t r u of xi tau, okay, mod x minus xi square t minus tau square. Okay, so this is the function which we are defining. Okay, this is the function which we are defining. So this function is of course d xi d tau, that part is there. Okay, I'm not writing anyways, I may or may not write this part, so please bear with me there. So this can be written like this, no, 1 by r power n. Yeah, of course there is a double integral here. If you want, you can write a double integral or you can just write a single integral. It is up to you. If you feel comfortable, let's just write a double integral, if you want. So let's just write, single integral is also fine. Yeah, it's not a problem. So this means that double integral of xi tau in e 0 0 r. See, e x t r, we have written e of x t r is just a translation of e 0 0 r. So the heat ball around the origin is translated to the new origin is xt. So I can just write it like this. Then I can just translate this thing. Yeah, translate this particular what can I say, function. Yeah, to something like this, u of x plus xi, okay, and t plus tau. This one is mod xi square by mod, no, there is nothing mod here. Mod tau square. There is no mod here. Don't worry about the mod. Okay, tau square. Okay, and of course that those things are there. Okay, d xi d tau. That's there. Okay, now. So this is just a simple translation. I'm just translating it. I'm quite sure you guys can. I don't have to write every single line here. Take x minus y equals to x minus xi equals to some z or something, and you can just write it like that. So that's there. Don't worry about it. So this is equals to double integral. Okay. By don't worry about it, what I mean by this is, please check this part. This is trivial, nothing to check here, but please, if you find that this is not this is not straightforward for you, then please go ahead and do this. So this is equals to xi tau in e 0 0 1. Okay, now I will explain to you why we suddenly see. Basically, if you remember, in the case of Laplacian also, we started out with a phi of r, right? We defined it. And after that, what we did is we looked at phi prime of r and showed that phi prime is 0, right? For Laplace equation. Here also we are going to do something similar. Okay, so here what we are, and to do that, first of all we have to make this function, the integral, independent of r. If you remember, in Laplace also we did the exact same thing. Here also we are going to do the exact same thing. Okay, So so the r is 1 here. If you do that, then it's just scaling in this variable, right, in the xi variable. So this will become x plus r xi and t plus r square tau. Okay, I'm not doing anything, I'm just replacing. So basically r this xi I'm taking, I'm just scaling it to r xi, and tau I'm scaling it to r square tau. That's all. Okay, so once I do that, you see what is d xi in this case. There is r power n xi d xi. Okay, d xi will get converted to r power n d xi because of the Jacobian part, Jacobian of translation. And here, so this will be, you see, mods, nothing will change here because xi is getting translated to r xi. So there is r square xi square, and after that here it will be r to the power 4 xi eta square, right? Okay, so 1 by r square will be here from here, this property, and the okay, am I clear here? Let's just write it. It will be, otherwise you guys can get confused here. So see here, this d xi, if you change here, due to the xi is in Rn, so if you are changing xi to r xi, there is a Jacobian which is r power n d xi, and from here tau is in r, so this is r square d xi d tau. Yeah, I'm sure you guys understood what is going on. Because of this change of variable, there is this Jacobian part, so that is why this r power n r square is coming, r power n d xi r square d tau. Okay, now you see this r power n and this r power n is gone. Okay, this r square r power n 4 is gone. So essentially we are only left out with, let me, I don't want to write it again because this is the same thing. Okay, okay, so let me write it this way. This is equals to this particular thing times d xi d tau. Clear? Okay, so this is how we are going to get. So I hope you understood what we did. This is the change of this is the change of variable formula. Okay, and I am going to use this formula again and again in this part. I am not going to always explain why this r power n and all of that is coming. You understood, huh? If you want to do it yourself, please check it yourself anyways if you are not convinced. Okay, change of variable, but I am not going to do it all the time. I think this is quite clear here how this is coming. We can go back from here to here, or we can come back from here to here. This same sort of calculations we are always going to do. Okay, so I urge you to please check this calculation first. Okay, so once that is true, then now I want to take what my differentiating thing. So differentiating. So see again, as I have explained to you, why we are doing all of this. I want to make this integral independent of 1 because I want to take phi prime of r. If this integral depends on r, then we are in trouble, right? So if I am taking phi prime of r, I can just take the integral inside, right? The derivative inside the integral if this integral is independent of r. Okay, so that's the idea, that's the motivation behind doing all that scaling and all. Okay, so differentiating, we have phi prime of r, that is equals to integral xi r, this in e of 0, 0, 1. Yeah, so first thing first, what is the derivative of u? So I have to take the derivative of this. Okay, see, this is the only function which depends on r, right? This does not depend on r, so I don't have to worry about it. This only depends on r. So if I am taking phi prime of r, by chain rule, what is this? This is gradient of u dot r, right? Dot psi with respect to r, dot psi plus u of t times r square, right? That's what we are going to get. Okay, sorry, not r square, 2r with respect to tau to r. Okay, so let me write it down here. So this is gradient of u at the point x plus r xi t plus r square tau, okay, dot xi, this is the xi, okay, because the derivative is with respect to r, in this case dot xi mod xi square by r square, okay, d xi d tau, okay, d xi d tau, plus there is another term. Because of the chain rule, I have to take the derivative with respect to t also. So plus ut at the point x plus r xi t plus r square tau mod xi square plus r, and there is the derivative of this, yeah, derivative of this. So this is 2r. Where is it? What can I write here? Maybe I can write 2r, okay, 2r. So that is there, okay. Of course that d xi d tau, okay, I may skip this d xi d tau all the time. I'm writing the exact same thing, okay. So double integral, I mean it does not matter double and single integral, again I mean repeating myself, but exactly the same thing, yeah, you don't worry about all that. Sorry, this is not r, this is tau, no, this is tau, yeah, I forgot. So maybe mod xi square, not r, tau square, huh? Sorry, this is a small mistake which I am doing. This is tau square, this is tau, okay. So what I want you to do is please check this calculation. I mean this is nothing special, I mean this is the very easy calculation. It's just a chain rule, this is just a chain rule. Okay, now once that is true, then again by chain rule what we can do is I can just shift this to r, okay, shift this to the r ball, r heat ball. So what I am saying is this: if I shift it, you see, while going from r ball to one ball, you have 1 by r power n vanishes. So while going from one ball to r ball, 1 by r power n reappears. Exactly the same sort of change of variable will work here, right? So now double integral of xi tau, okay, this is not r, this is tau, xi tau, and in e of 0 and r, okay, this is gradient of u x plus xi t plus tau dot xi mod xi square by tau square. That part is there, I am not writing all that, yeah, I mean that is, sorry, I already wrote d xi d tau, no, forget about d xi d tau, because this is already there, I mean always, okay. So that is that part is there, plus I'm not writing all that d xi d tau, I'm just skipping this part. So 2 by r power n plus 1, yeah, this is also coming. Again, why this is coming? So this is again a change of variable, please I mean verify this is true. I am quite sure that is not a very difficult thing to verify, but please do that, because of this tau and all, I mean this because of this property, I mean if you break this thing, the reverse change of variable, then you are going to get 2 by r power n plus 1. Again, I am really sorry about this external flight, these plane noises. Ut of x plus xi t plus tau mod xi square by tau, okay. So I can write it like this, and this is this clear? See, how am I getting this property? Again, I am just reversing back. 1 by r power n plus 1 is because of this term ut. I mean if you just reverse this part, you can find there is an extra r here, so that is why that problem, okay. So now let us focus on this property now. So let's say a plus b, let's define it, a plus b, okay, this is a, this is b. Now focusing on b, what we have. So on b, what we have is this: it is 2 by r power n plus 1, okay, integral xi tau in the heat ball of radius r. We will call it like that. There is no radius, but let's just call it like r, called radius r. Okay, ut of x plus xi t minus t plus tau. Okay, mod xi square by r. This is equals to 4 by r power n plus 1 integral xi tau in E0 0 r. Okay, ut of x plus xi t plus tau gradient of xi gradient of phi xi tau dot phi dot xi. Okay, now you may be wondering, where am I getting all of that? Okay, where am I getting? It's not very difficult to see that what is gradient of. So since I am writing this term like that, okay, since gradient of what do I call it, phi, gradient of phi at the point xi tau, if you calculate it, this is becoming xi by 2 tau. See, where is phi? Phi is here, right? I defined phi somewhere, no? Where did I define phi? Phi. Okay. Phi of is this, right? So if you take the derivative of this thing, the gradient of phi, you can just say that is going to be xi by 2 tau. Okay, the gradient of phi. That's what I wrote. Where is it? Yeah, that's why that's why I wrote. Gradient of xi is phi. Gradient of phi at the point xi eta is phi by 2 tau. Okay. Right. Now, so once that is true, then so let me put it. This is fine. So once that is there, we have 2 by r power n plus 1 integral xi tau in E0 0 r ut of x plus xi t plus tau mod xi square by r. Okay, this property, this the function which we got earlier. Okay, this particular thing is 4 by r power n plus 1. Let me again write it. It will become much clearer. Integral xi eta in. So this is very calculative. The proof of this. So please bear with me here. Ut. This is what I just did in the last page. I just want to do it here. Otherwise, I may get confused. This is t plus tau, and then I had what is it? Gradient of xi dot. Okay. This is gradient of xi at the point xi tau dot xi. Okay, that's what I have. Now this is, I can write this particular thing as 4 by r power n plus 1 integral or double integral or single, whatever. I am just writing single. Xi eta in E0 0 r. Okay, and see u solves the heat equation, right? So ut equals to Laplacian u at that point, right? So essentially this means that it is okay, we don't have to use that. What we are going to do is, I am going to use a different property here. What I am going to do is, I am going to do it like this. So let's say divergence of ut x plus xi, okay, t plus tau. Let me write it and then I will explain why am writing it like this. Xi tau xi, this particular thing, minus xi of phi of xi. I'm sorry, this is, there is lot of phi and taus are there, so I'm this is gradient of ut, okay, at the point x plus xi t plus tau, okay, dot xi minus n xi of phi of xi eta u t of x plus xi t plus tau. Okay, this is there. Yeah, this is fine, I think. Yeah, this is fine. Okay, now let me explain to you why all of this is coming. Yes, see, if you take the divergence of this thing, then first you have this particular thing. Yeah, I mean, you take, so this is basically, you know, the Leibniz property kind of thing. Yeah, so divergence of this is, first of all, you take this and you take the gradient of this, which is this part, and then you have the other two things. So basically this will be there, and then divergence of ut, which is Laplace gradient of ut at that point, dot psi, and then you have divergence of psi, which is n. So minus n times it will remain unchanged, ut and psi. Okay, so is this clear? So essentially what am I doing? I am doing divergence of UVW is UV divergence of W plus, you understand, right? Plus V W divergence of U plus, and it goes on like that. So basically this is the Leibniz rule. This is what I am using here. Okay, okay, once I do that, then what do I get? Then I get something like this. So this okay, this part is, let me write it like this. So minus 4n by r power n plus 1, okay, integral xi eta in E0 0 r, okay, xi phi of xi eta, okay, ut at the point x plus xi t plus tau, okay. Just take a minute and think of why all of this is coming here. Xi tau in E0 0 r, okay, phi of xi tau dot d tau of, I will explain why all of this is coming here, x plus xi t plus tau dot what is it, this I am doing, so this is dot xi. Okay, okay, fine. Yeah, okay, so let me explain to you how all of this is coming. What happens to this divergence of this particular thing? This, see, divergence, this is a region which is a smooth region. Divergence of this function, let's take this function as some function phi. So divergence of phi on this thing by divergence formula, Gauss divergence formula, this is equals to this function times eta on the boundary, right? This functions times eta on the boundary, yeah, on the boundary daily, yeah. And what happens to phi on daily? Okay, see, this is true since phi restricted to del E 0 0 0 r is 0. That's a beautiful property. Del E of 0 0 r, that is equals to 0. Okay, see, phi is defined like that. Actually that's definitely going to be true. Yeah? Phi is defined like that. Phi, this psi, sorry, phi, not phi, psi, or phi, I mean calling this phi, right? Yeah, so phi is defined like that. So you see, phi, if you want, you can just check it yourself. Phi is essentially going to be 0 on the boundary of the ball E 0 0 r. Okay, so please check that part. This is phi. where is it? Yeah, so please check this. Yeah, check. If you are not convinced, please check this part. So since phi is 0 here, from Gauss divergence, what do you have? See, let me write it here. From Gauss divergence theorem, okay, what do I have? Yeah, divergence of integral over omega, divergence of u, let's say, yeah, or gradient u. I mean, what do you want to call it? Whatever. Yeah, divergence of gradient u, let's say. Yeah, that is a divergence of some vector field. Yeah, not gradient u. Let's just do it for a divergence of a vector field. Let's say something u. Let's call it a u. This is equals to, on the boundary, u dot gamma ds. Gamma is the unit outward normal, right? So that's the Gauss divergence theorem. So you see here, divergence of this particular thing is basically this is your u here, huh? The thing, and that u on the boundary, this psi is on the boundary 0, so that is why this particular term is gone. Now I am just left out with this term, okay? And how am I getting all of this? So first thing first, minus 4n by this thing is this term, this particular term is this term. I'm just writing it like this, yeah, minus 4n by r power n plus 1, and this whole thing I'm just writing it down. I'm not doing anything else, huh? This particular term, I am just writing it in this way. Are you convinced that this is true? Of course this is true. Yeah, why is this true? Because I mean, you can just take the derivative here, right? And if you take the derivative here, d with respect to tau, the first by chain rule, the first term is not going to be there. From in the second term it will be there. So the if you use chain rule here, of course it will be gradient of u t at the point t plus tau, x plus xi t plus tau, and then this xi is there, so that xi is there, okay? So this is just a chain rule from here to here, from okay, how do I put it? This particular thing to here, okay? So this is the chain rule, okay? So I'm sorry for see, these are big calculations, okay? So I'm sorry if there is a little mess here, so please bear with me. Okay, now I have this thing. Now I want to look at what am I doing here? This function, this thing is here, and that is here, okay? Now we consider this second expression, this expression, okay? So let's say this is c plus d, so I will consider this last expression, okay? So considering this expression, integral xi eta in E0 0 r, I am writing this all the time here. This is phi of xi eta times del tau of du at the point x plus xi t plus tau dot xi. Clear? So this particular thing, this term I am considering the second term in this or the middle term of this expression, okay? So this term I am considering. So this term by I mean, you can use the integration by parts formula, right? Here I am using integration by parts formula, so that will give me minus integral, okay? Hey man, I'm not writing this thing, yeah, that is. So that is there. Xi eta is in E. I am writing it too many times, huh? So it's assumed that xi eta is in E00R for now, okay? So if that is the case, it will become xi tau with so I am taking the derivative on the other part, integration by parts. Derivative is getting transferred here, okay? Xi tau at the point phi tau at the point xi eta, and then you have du at x plus xi t plus tau, okay, dot psi. That thing is there. So this is the term. Okay, let me write it. It is better. Otherwise, you may get confused here. E00 r, and there is a boundary term. Okay, plus boundary of E and this term will be evaluated without the del tau xi times gradient of u on the boundary, and on the boundary xi is 0, so this particular term is 0. Okay, not there. Clear? So the second expression is equals to minus of this particular term. Okay, and this term, so this small calculation has to be done. Maybe I can skip the calculations here. See, phi is given to you. You guys already know what phi is, so you can calculate phi tau. Okay, so please check this part yourself. I am just going to skip this part. I am going to write it like this. So phi, so this is equals to minus integral xi tau in e 0 0 r, okay, and minus n by 2 r minus mod xi square by 4 tau square. Okay, and then you have gradient of u x plus xi t plus tau dot xi. Clear? So that is there. So how am I getting this? I am just taking the derivative of xi with respect to tau, phi, derivative of phi with respect to tau. Okay, and then I get this. So please check this part. Again, this is not very difficult to check. I mean, this is usual stuff. Okay, now we take this expression. Now we take this expression, and this expression we just wrote it like that, right? So I'm just rearranging all the expressions. Okay, so if I rearrange all that, so rearranging all the expressions. Okay, what do we have? I have phi prime of r. Okay, so is equals to minus 4n by r power n plus 1. Okay, integral, again I am not writing, it is e0 0 r, phi of xi eta ut of x plus xi t plus tau minus 2n by r power n plus 1 integral that part, what was there, this one, right? Gradient of u at x plus xi t plus tau dot xi by tau. Okay, so this is equals to this. I'm just rearranging this thing and writing it down. I'm not doing anything special. So this is equals to minus 4n by r power n plus 1. Okay, again integration by parts. I will just do integration by parts ut. Okay, am I doing it correctly? One second, let me just check. This part is there. Yeah, this is fine. Yeah, so yeah, okay, so this is integral. Minus sign I won't need because I'm using integration by parts here. Derivative will go here, so the minus sign is getting cancelled, and then I have psi t at the point, phi t at the point psi and eta. Okay, and then you have u at the point, so it is becoming gradient of u at the point x plus xi t plus tau. Okay, and minus 2n by r power n plus 1. Okay, and this integral it is becoming gradient of x plus psi t plus tau dot xi by tau. Fine. Yes, I think this is fine. I am not making any mistakes anywhere. I think it is fine. Yes, this is fine. Now, one second. Let me just check. Yes. What is u xi t? Phi t. Phi t is gradient of phi is xi by 2 tau. Okay, gradient of phi is xi by 2 tau. So sorry, this is gradient, this is gradient of phi. It's not only with respect to t, but this is gradient of phi. Gradient of phi at the point zao tai. Okay. There was a mistake here, so please check this part. So again, check this part. Okay, so from here to here, please check this part. Okay, so once I have this, then I can write it like this, now I'm missing something. No, I'm not missing anything. What is gradient of yeah, okay, yeah, gradient of psi, that's what we calculated somewhere, no? What is gradient of psi is xi by 2 tau. Okay, so you just put xi by 2 tau here. You see, xi by 2 tau, so xi by tau, and 2 by 2 tau is there, so it will become 2n by r power n minus 1, so minus 2n by r to the power n plus 1, and this term will get cancelled out, so this will become 0. Okay, so this will become 0. So hence, therefore, what it means that phi of r is constant. Okay, that's what. So after so much effort is required to prove this, and we at last proved that phi is constant. Okay, so with that much effort, we have proved that phi is constant. So phi prime is 0, phi is constant. Okay, and therefore, phi of r, this is of course limit r tends to 0, because phi is a continuous function, right? And u of x plus r xi t plus r square tau, okay, mod xi square by r square. Okay, this is equals to, if you just take the this is in e 0 0 r, sorry, 1. I'm taking the r here, so 1. On this limit r tends to 0, if you just push it inside, yeah, you can actually show that since the u has a continuous property, it will look like this: u of xt, and this is e 0 0 1 mod xi square by r square. Okay, sorry, not r square, tau square. Okay, d xi d tau, that is there. I have skipped all that d xi d tau part here, so that is there. Yeah, now here it is still not done. Yes, and I am going to take a liberty here, and I am going to assume that this particular thing, this mod xi square by mod tau square, this thing is nothing but 1. This is 4 r power n. Sorry, is this clear? Okay, so I really feel bad about it, but let's just stick with this. So this is a lemma due to if I recall, Fuchs. Okay, so this is u of xt. Is it clear? This integral, I am not calculating this integral, okay, but this goes way back to 1961 or something. There is a paper by Fuchs where he has proved this property. Okay, this is not a very easy thing to prove, so I am going to assume this. Okay, so with this we are going to end this lecture. So we have proved what we wanted. Thank you very much.